question, how low a voltage can I use, right? And what is the lowest voltage I can use? Now, in a lot of some of the textbooks, actually, you see the voltage, minimum voltage that you can use is kind of specified as sum of the threshold of the NMOS and PMOS and so on. That is really not the case. In fact, you yourself in your exercises have probably found that your ring oscillators and circuits can run down to much lower voltages, much below the threshold voltage of the transistors. So we look at this concept of deep voltage scaling, and also this concept of minimum energy point of operation, and basically see what are the practical limits of voltage scaling, and then we look at how do you do circuit design for this very low voltages. So these are things which we'll cover over the next few lectures, which we won't cover everything today in this lecture. Right? So first, let us look at this question, try to answer this question. What is the lowest voltage I can operate my digital circuit at? And it turns out that it's not that hard to answer that question. It's a very interesting question, but it's also quite straightforward for you to answer that question using whatever you have learned so far. And anytime you ask any question about digital circuits, you kind of want to, any such theory type question on digital circuits, first you want to have a simple circuit to use to understand and analyze that question. And the simplest circuit you can get is an inverter. And largely whatever works for inverters in some sense also works for other CMOS gates, because other CMOS gates is just a generalization of an inverter with a little bit more complexity in terms of the PMOS pull up and NMOS pull down stacks. So you look at first the inverter, right? You have the inverter, and you have this DC switching characteristics of the inverter, where what we have plotted is the output voltage as a function of the input voltage under DC conditions. That means you have a particular input voltage, you see what is the output voltage. And you have seen this kind of a step type DC transfer curve, where at the origin this is 0, and here you have the maximum VDD which you put to the inverter. So when the voltage is 0, you have the maximum output voltage, close to VDD. Now, one of the important thing is, so basically what will happen when I reduce the supply voltage, right? So when you reduce the supply voltage, essentially what you're doing is you had a design which had a higher supply voltage, and you have reduced the supply voltage. So in some sense you have shrunk. You can think of it as scaling down this DC transfer curve. Okay, except it's not like a perfect scaling. What happens is that there is a degradation out here of the slope. When you actually do this, you'll find that here you had a sharp slope, but as you scale it down, the slope reduces. So why is the slope important? The slope is very important because if you recall from the digital VLSI class, that any digital logic, you need to have sufficient noise margins. That means the output voltage level, which is considered as logic high, that voltage level should be higher than the voltage level of the next gate, the input voltage level, the input logic high of the next gate. So that, when the output high is higher than the input high, there is margin. So that when the output gives a voltage which is considered to be high, the other guy can interpret it as a high with some voltage margin. And that voltage margin is essentially governed by the slope out here. The sharper the slope, the larger will be the noise margins. Conversely, when the slope degrades, the noise margins for high output, the logic levels will not be very good. So intuitively also the worst will be when you just have a 45-degree line. Right? 45-degree line is slope of -1. So, it's kind of, everything is okay. Whatever input you give, you kind of get output which is not, too far off in some sense, right? Whereas here, there is this band out here when the input is less, the input is less than this particular value, the output voltage value is much higher. So it really separates it. And having this gain, the absolute value of the gain bigger than 1 is important for you to be able to cascade logic gates. Right? Anytime you build a big digital circuit, you have a number of gates which you are cascading. So, you need to have this property of restoring the logic levels, which you get only when the magnitude of the gains is higher than 1. So now it becomes very simple. You have a clue as to how to answer this question. What is the lowest voltage level at which I can operate my digital circuitry properly? Okay, so one bound for that voltage level is a voltage level where the gain just from having a magnitude bigger than 1 becomes equal to 1. So I need to have a voltage level above that particular value, right? Because as I reduce the voltage level, the curves shrink and the gain decreases. Now, so really now the problem comes down to having a formula which relates the voltage level to the gain, right? We are talking of the gain at this point. So you have a 45-degree line, you find the gain at when the 45-degree line intersects this curve. At that point, you find the gain and relate it to the voltage level. Now, how do you calculate the gain out there, right? So to calculate the gain, you have to go back to the equations which relate the currents and the voltages. So now we know that these voltages will be very low, will be less than the threshold voltage of the transistor. So the governing equations for the current will be the sub-threshold equations for the current. Now you have a number of leakage currents. We are only concerned with the current which is the sub-threshold leakage current, ID, which flows between drain to source. You have some junction leakage and you have some gate leakage, but these are not currents which determine the DC characteristic of the device, right? So if you look at the and also the gate. So if you look at the sub-threshold current equation, you have the sub-threshold current equation is essentially you have a W by L term which is related to the size of the device. Width of the device is W, L is the length. You have the gate overdrive VGS minus VT. VT is the threshold voltage, VGS is the gate to source voltage. This is the gate overdrive divided by NVTH. VTH is the thermal voltage, KT by Q. N is the related to the sub-threshold slope. It's usually a number between 1 to 2. And it kind of tells me, you can think of, it kind of gives an indication of how much control the gate has on the channel. Because your channel has multiple masters, including the drain, the bulk, and the gate. Right? So the potential on any of these can influence the state of the channel. And all of these guys can control how much the channel is inverted. So this kind of captures that. And then you have this term 1 minus e to the minus VDS by VTH, which basically tells me that this current is also controlled by the VDS voltage. Remember, VDS also affects the threshold voltage. That we are not considering out here. That is a separate factor. VDS has an impact on the threshold voltage, and in that way also it can control the current. And of course, this is mu0 is the mobility of the carriers in the channel. Cox is the unit capacitance, which is essentially 1 by T, epsilon by Tox. Epsilon is the dielectric constant out here. Tox is the oxide thickness between the gate and the channel. And this is the same N here, and again this is the thermal voltage. So this is the equation which relates the gate source voltage to the sub-threshold current. Now these factors, mu, C naught, N minus 1 VTH square, we can kind of club it together as I naught. And then I'm just pulling out e to the minus VT by N VTH. This term I'm just pulling it out. And then I'm just left with the two terms, two groups here. One group is independent of the gate source voltage. Other group depends on the voltages at the nodes, the gate source and the drain node. So when I do that, I can club all of this together as a factor called beta, okay, times e to the VGS by NVTH times this. So beta is now just a term independent of the voltages of all the nodes. And beta in some sense is the drive capability of the transistor. Now typically in super threshold operation, the drive is controlled basically by the width and the sizing. And then of course there is VGS minus VT, so by reducing the threshold voltage you can improve the drive. But here again the same concept, you can control the width and the length and as well as the threshold voltage. All of them kind of tell me what is the drive capability of the transistor. The actual current of course depends on the actual voltages. This is like a proportionality constant. You can, by upscaling the size or reducing the threshold voltage, you can increase the drive strength of the transistor. So now for us to calculate the lowest voltage limit, what do? We basically look at the intersection of this 45-degree line to the DC transfer curve, and we ask the question, what is the gain at this point? Okay. Now to calculate that, you look at this at any point here in this DC transfer curve, whatever current is coming from the top has to go down to the bottom. Okay, so IP is all equal to IN, right? So this is true for any point on this DC transfer curve. So IN is beta n e to the Vi by n VTH. Vi is the voltage, so VGS is equal to Vi, which is gate minus source for the NMOS. So e to the Vi by n VTH times 1 minus the VDS for the NMOS is V0. Right? 1 minus e to the minus V0 by VTH. So this is the current in the NMOS transistor. That current should be equal to the current from the PMOS transistor. So that current is okay. So what we have is the current in the PMOS is given by beta P, which is the drive for the PMOS, e to the VDD minus Vi, right? Because the gate source voltage for the PMOS is this difference, VDD minus Vi, right? That is the gate source voltage by NVTH. Remember the VT of the PMOS has been pulled into the beta P term, right? As we did last time, I mean in the previous slide, times 1 minus the VDS, e to the minus VDS. VDS is this, VDD minus V0 by VTH. So this is the equation for the PMOS current. Now the NMOS and the PMOS currents should be equal at any point on this curve, right? So what we do is we basically, and then just to simplify the arithmetic and the calculations, we'll assume beta n is equal to beta P. Okay, so when we do that, now how do we go ahead and solve this problem? I'll leave this as an exercise for you to, from this equation, get the gain value for you to calculate, and you'll find that the gain value that is essentially given by some term like this, 1 minus e to the minus VDD by 2 VTH by e to the minus VDD by 2 VTH. So essentially you have to go through and calculate the gain, some arithmetic and algebra, not arithmetic, algebra, you have to do some manipulations and you'll get the gain. Now this mod of this, the magnitude of this gain has to be bigger than 1. So you put this bigger than 1, the magnitude, that means this minus goes away, and you rearrange the terms, you will find VDD, that is supply voltage, has to be at least 2 log 2 times the thermal voltage. So what this is saying is that, and the other thing you notice out here is that we have not made any assumption about technology. There is no channel length here, there is no oxide thickness, nothing, doping, nothing is there, right? So it's just a very general expression, independent and applicable to any technology node. And you get this equation, this constraint that the supply voltage has to be at least this much, which if you calculate is about 37 millivolts. So what this is saying is that at least from this simple model, the supply voltage, minimum supply voltage, which you can use to operate your digital circuits, can go as low down as 37 millivolts. This is very, very deep subthreshold operation. Now this is something which was first pointed out in a paper in 1970s by Swanson and Meindl. They did some calculation. Of course, they got a number which is very similar to this. And since then, a couple of other people have also reported numbers like this. And it was kind of initially not much attention was paid to this because it's just an interesting curiosity. That's all. What do you do? But with this advent of all these variables and ultra low power devices, it became very interesting to kind of go back and look at this question. How low can I go in my supply voltage? And early 1990s, a lot of activity started happening to experimentally get to this number, right? And so there were people who in the laboratories could demonstrate circuits operating down to 100 millivolts. Now there are also some laboratory demonstrations which show circuits operating down to even less than 100 millivolts, about 80, 90 millivolts and so on. So this is something which is also borne out from experimental considerations. As well as it turns out there are certain other ways of arriving at some similar number using thermodynamic type arguments. So some physicists have also looked at this problem and come to similar numbers. That means you need to have a voltage which is a few times the thermal voltage. Thermal voltage is 25 millivolts. Now, why is this kind of interesting, right? This is interesting because when I operate at 1 volt and I scale it down to 50 millivolts, CV square, right, half alpha CV square, that is the dynamic energy, right? So the ratio of the voltage, if you take, then that will come down to, that will give me the ratio of the dynamic energy. So I can save the energy by 400 times. So that's a lot of savings in energy if I were to able to operate from here to here. But there is a downside. Downside is speed. Because as I reduce my supply voltage, the gate overdrive VGS minus VT starts reducing. Right? So of course, initially when I'm in the super threshold region, the current is proportional to some function VGS minus VT, which is either VGS minus VT square or VGS minus VT raised to alpha, which is some number between 1 and 2. As I get down to subthreshold voltage, again I have e to the VGS minus VT. But VGS minus VT is the overdrive which reduces as I reduce VGS. Why? Because as I reduce VDD, VGS will also reduce. The gate voltage applied to the transistor for the next gate is essentially the VDD. So my speed will degrade, and it can degrade down by quite a dramatic amount, 10 to the 4 type, 4 orders of magnitude. So what could run at 1 gigahertz at 1 volt can end up running at 50 kilohertz at 50 millivolts. So it's a very, very low voltage. Now, the reduction in energy we have talked about is only for dynamic energy. As you know, leakage energy, which is essentially the energy which is just getting lost because you have connected something to the leaky circuits to the power supply. That is, leakage current is continuously flowing. So for the entire duration, leakage energy will be happening. You'll be losing energy due to leakage. And as you recall, as you go slower and slower, the leakage energy per operation will go up and up. Why? Because for the same operation, you are taking more time. So what this means is that you have to also watch out for the leakage energy. While you reduce the dynamic energy, your leakage energy will go up. So it doesn't necessarily mean that just because you can operate down to 50 millivolts, you should run it at 50 millivolts. Okay, it's just saying you can make things run at 50 millivolts, but it might not necessarily be the right thing to do for you from an energy perspective. Finally, this performance is such a low performance. Is it really useful? 50 kilohertz, is it kind of interesting? What to do? Right? Now, we'll see that actually this performance, what we'll find is that as we scale technology, 65, 45, 32, 22, 14, etc., this performance also improves. So, so you can now very easily reach 30, 40 megahertz of operation running in subthreshold for some of these advanced nodes. Right? And what that opens up is a lot of applications. If you see any microcontroller which you are using, they run at a few megahertz, right? 8 megahertz, 10 megahertz, that kind of thing, right? 16 megahertz. So a lot of these applications where if you are able to run in the low megahertz, you are now, as far as the performance requirements of the application are satisfied, those now become open to this kind of approach where you do very deep voltage scaling, where you scale down the voltage to these kind of sub-threshold levels. So, so I'll kind of stop here today. We'll kind of follow on from this in the next class and kind of see, look at the issue of balance between energy of dynamic and leakage, and then what are the practical limits and so on. Before I close, any questions?
Assuming that eta, which is the ratio between the depletion capacities and the oxide capacities, but both the PMOS and NMOS, they are same. Is that so? Are they same?
They will see that ratio depends on the ratio of the gate capacitance to the body capacitance, and the body capacitance will depend on the doping level. So they need not be the same, but they will be kind of very close together. So you can, for this at this level of analysis where you kind of want the numbers simplify, you can do that. Otherwise, your calculations become very hard, and these equations, you cannot solve it analytically. You'll have to numerically solve the equations because they are not